Okay, let's continue to understand density matrix by looking at how the mixed states are represented on Bloch sphere. Okay, and this is in the chapter 6 of the book. So let's first just do a simple example to get a taste on what a mixed state density matrix might look like on Bloch sphere and what is its meaning. Okay, so let's consider this density matrix, which is hold on. So let's consider this simple mixed state, if you remember. So we say that we might have a mixed state. Which is given by alpha square percent of 0 and beta square percent of 1. Right? So this is a mixed state. It's a mixed state composed of two pure states, 0 and 1. So what is its density matrix? Yeah, it is equal to alpha. Sorry, I say the wrong thing. It's not alpha square. It's just alpha. Right? So alpha can be 0.1, beta can be 0.9. They should add to 1, right? So this is the probability. If you remember, this is the case that when you look at the density matrix equation, we have I equal to 0 to k minus 1 p1, and then the outer product of pi, outer product of psi I, right? So basically, this is P0, this is P1, and this is psi 0, and this is psi 1. Okay? Then, of course, then, yeah, as we already showed you, by using this equation, we're going to have, say it wrong again, it should be outer product of 0 times plus beta outer product of 1. Okay, and we already showed last time, you can just go through the process. This gives you 0, alpha 0, 0 beta as the density matrix. Okay, and we also know because density matrix is a Hermitian 2 by 2 matrix, so it can be decomposed as the I, right, plus A dot sigma divided by 2, right? Where we have used A instead of A dash now after the last video or lecture, right? Which is equals to I plus A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3 divided by 2. And again, to remind you, so-called 1, 2, 3 are just X, Y, C, the Pauli matrices. Okay, so this density matrix can be represented in this way, right? So we can decompose it, but as an exercise, we can also use the inner product of matrix to find out what is A1, A2, and A3, right? Just for example, just as an exercise, we know that A1 is going to be equal to the trace of sigma 1 times rho, for example, right? So what is sigma 1 times rho? Just go over the process. It is sigma 1 is sigma x 0, 1, 1, 0 times alpha 0, 0 beta, which is equal to the trace of if you just go through it, this is just 0 beta alpha 0, right? Which is equal to 0 plus 0 equal to 0. So it means A1 is 0. Similarly, A2 is also 0, okay? Let's look at A3. A3 is the trace. Again, this, if you forgot, right? Again, why I do trace? Because this is just the inner product of the matrix times row, the inner product of matrix and row, right? They are equals to the trace of sigma yi row, dagger, of course, but it's Hermitian, so it's the same, and divided by 2. Okay, I believe so. I think I'm using the right equation, right? So that A1 divided by 2 equals trace divided by 2. So go back to the original equation. I think I'm correct, right? So that's why this is sigma 3 or sigma z equal to the trace of 1, 0, 0, negative 1 times alpha 0, 0, beta. Now this time we got something because it is equals to alpha 0, 0, negative beta, and the trace is just equal to alpha minus beta because trace is the sum of diagonal. So this is the trace. So because of this, I can say alpha, which is equal to, rho equal to alpha 0 beta 0, 0 beta is also equal to I plus alpha minus beta times sigma z, which is sigma 3. Right? So I decompose it into a linear combination of the identity matrix and the sigma z matrix. Okay, and definitely I can also say something. I can say that A in this case is just equal to 0, 0, alpha minus beta, right? Because I did not show A2, but it is 0 if you try it. So A, which is the vector, is just 0, 0, alpha minus beta. This is A, the A vector, right? So then I have a question, right? So my question is, what is the expectation value of sigma c in state row, right? So for state row, what is the expectation value, right? So from this, what was given, which is 8% of 0, and then, so not A, but alpha percent of 0, beta percent of 1, then it means the FH value, when I do the measurement, because I have alpha percent of 0, this will give me 1, right? When I do the measurement, the state, the eigenvalue is 1. It may give me 1. But at the same time, I have beta percent of chance, right, of getting negative 1. And maybe when I say percent, this one actually confusing everyone. I should not call it percent. I should not add the percent. I'm sorry for that because it is 0.1 is 0.1. Of course, 0.1 is 10%. So I better just use number. I call it 0.1, right? Or maybe, yeah. So how about or you multiply 100%, right? Maybe I just put it now. I think you understand what I mean, right? Beta part, alpha part, right? Beta part. You have so much of this, right? Right. So or here I can say this is like alpha divided by, not divided by, right? This is like alpha times 100% and beta times 100% of what? That might be better, right? But anyway, this is the FH value. This gives me alpha minus beta, right? So I will expect this if you try to ask me what is the expectation value of this, right? Then from here, what do I get? Then I just say that this A vector is along the Z head, right? Because now this Bloch vector is like telling me that I have a location, like let's say I have a alpha percent of 0, not alpha percent, alpha times 1, alpha times 100% of 0, right? And then I have beta times 100% of 1. So it is nice saying that, yeah, you have this vector, but you only have alpha part, right? You have the alpha part. And I also have another vector, maybe like this. I have beta part. It's not full, it's not 1, right? These are all smaller than 1. And then the net effect is that I have a vector. Let me use this color. I have a vector which is alpha minus beta pointing up, right? Of course, it's negative, then it's pointing down, right? So it looks like to me that alpha, this A, it looks like to me that A, right, is along Z, and it also represents the expectation value of sigma C. Right? Do you see that? Instead of sigma C. Right? So in this simple example, we already know that for pure state, the Bloch vector will have a length of 1, and it is on Bloch sphere. The Bloch vector is at the point pointing at the state of the pure state. But how about a mixed state? What is it? Now we take this simple example, which is just a mix of 0 and 1, and they have certain bar, they have a weight for each of them. We found that the Bloch vector A, right? We're talking about Bloch vector. So this is the main point that we're trying to understand. The Bloch vector of this case, just this case, turned out to be the length along the z-axis. And its length actually is the expectation value if we were measuring sigma c. Do you see that? Now, for mixed state, for the same density matrix, it can be a mixing of many, it can be many possible mixing, not just this one. You actually can have an infinitely possibility because you can always decompose your matrix, right, into infinitely possible type of mixing to get the same density matrix. But here we'll just particularly show that effectively for this mixed state, it's just like that we have the alpha percent of 0, beta, let me just call it alpha percent, beta percent, although it's times 100%. Alpha part of 0 and then beta part of 1. Alpha 0 give me eigenvalue equal to 1. Beta give me eigenvalue equal to -1. And turn out that the length of this Bloch sphere represents the expectation value along sigma z of this mixed state. Okay, so this is first, of course, it needs to be shorter than 1. We know that already. The Bloch sphere, right? The Bloch, we already showed that a smaller than 1 for a mixed state. The Bloch vector will be within the Bloch sphere. Right here, we of course we prove this again. We show this again. But secondly, is that its length represent the expectation value of this density of sigma c for this density matrix. So then we're curious is it the same what is the meaning for a general density mixed state? So that is what I want to discuss next. Okay, so I would like to show that I would like to prove together that A, which is the length of the Bloch vector of a density matrix, okay, represent the expectation value of A dot sigma divided by A. Normalized, right? So I can call this A, instead of doing this, I can do it as an A hat dot sigma. So here, I normalize it, I make NA hat equal to A divided by A. Why do we do this? Because it is a mixed state. A might not be a unit vector, right? So it can be shorter than 1. So that's why we normalize it by dividing to its magnitude. So what I'm trying to say is the length of A is the expectation value of this operator. Okay, first, this is the first thing, right? This is what we want to prove for what is the meaning of A? Rho equal to I plus A dot sigma divided by 2. This is the general density matrix. It can be pure, it can be a mixed state, right? But what I'm saying that is that what is the meaning of the A? We know that it is shorter than 1 for mixed state, right? It represents the expectation value of this guy. Okay. For a density matrix rho, right? The meaning of A represents the expectation value of NA dot sigma. Okay. So let's see if that is true. All we need to do is just go through the math. So what is NA dot sigma? What is this, the expectation value of this guy? We learned that before. But by the way, if this is talking about the expectation value of this operator NA dot sigma for the density matrix rho, right? So this is just equal to the trace of NA dot sigma times rho. Right? This is the definition. So let's just keep plugging in. This is equal to the trace of NA. Sorry, this should be NA hat. NA dot sigma. And I just plug in rho, which is I plus A dot sigma divided by 2. So I will continue to do this. This is just equals to the trace, right, of, just do multiplication, NA dot sigma plus 1 over 2 NA dot sigma times NA dot sigma. It's getting worse. Let me just make it as a square. Right, do you see that? I say that the expectation value of NA dot sigma is just, of course, is by what we proved earlier in the last video, trace of NA dot sigma, which is an operator, times the density matrix. The density matrix is I plus A dot sigma divided by 2. Right? So you multiply this to here, you get NA dot sigma, good. And I multiply the whole thing is NA dot sigma, so I cannot use square, I'm sorry. NA dot sigma times A dot sigma. Right? So it's ugly, but hope you get it. Now, when we do trace, when you apply trace to this one, what do you get? This is just a linear combination of sigma x, sigma y, sigma z, right? So if you forgot, let's just quickly remind you what is, right? NA dot sigma, if I have a different component, I may have NAX times sigma x plus NAY times sigma y plus NAZ times sigma z. And if you take the trace is linear, you apply to each of them, but Pauli matrix is what? Traceless, right? So that's why anything dot sigma vector is going to be zero for their trace, right? So this is easy. So this becomes, so I just say this part is zero, right? So I take out the half, I have the trace, then I just expand a little bit because NA is just equal to A divided by the magnitude of A, right? And then dot sigma times A and then dot sigma. So this equal to 1 over 2 A magnitude, the trace of, now I can use square, NA dot sigma, then square. Now this is a little bit to evaluate, difficult to evaluate, right? But if we expand it, then you will see the result. Because what is A dot sigma again? Right? A dot sigma times A dot sigma. If you just spell it out, it is A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3, and then the whole thing times A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3. You see all this term, you have sigma 1 times sigma 1, sigma 1 times sigma 2, sigma 1 times sigma 3, sigma 2 times this, right? So you have all this cross term, you actually can write in a summation. I equal to 1 to 3, J equal to 1 to 3, and then you just call it Aij. No, just call it Ai times Aj, right? Because you have two coefficients. And then you have sigma I, sigma j. Correct? Now, by looking at this, if you're good enough, you already see that. Otherwise, you see that you either have sigma 1 go with sigma 2, sigma 3, or sigma 1 itself. But we already recall the equation, right? What did we learn earlier? We learned that the trace of sigma I, sigma j equals to delta ij. Right? So if your term are not the same, don't have the same unit, like sigma 1 times sigma 2, you will get 0 because they are not the same. Right? So based on this, you see that this term, if you take the trace of A dot sigma square, you will have, sorry, I forgot the 2 though. This has a 2 times delta ij. What do you get? You have 3 terms that will stay, right? Which is sigma 1 square, sigma 1 times sigma 1, sigma 2 times sigma 2, sigma 3 times sigma 3. Other terms will be 0 if after you're taking the trace. Right? So this one is just equals to sigma. Let me just go through the step carefully. This is equals to, let me don't apply it yet, okay? So this is equals to the trace. Because others are gone, I have A1 square, sigma 1 square, plus A2 square, sigma 2 square, plus A3 square, sigma 3 square, right? I also have A1, A2 times sigma 1, sigma 2, but the trace is 0, so they are gone. And based on this, I know this is 2 delta ij, so this is 2 for every term because trace of sigma 1 square is 2. Trace of a sigma 2 square is 2. Trace of sigma 3 square is 2. Oh, right. I need to erase this one. This is 2. Yeah? So because of this, then I get what? A1 square plus A2 square plus A3 square, which is equal to 2A vector square, right? Because the sum of their basis coefficient square is equal to the length square, right? So that's why I can say that the FH value of NA dot sigma equals to 1 over 2A magnitude times 2A magnitude square, right? Because I just copy this one to here, and this is the trace of this square, so it is equal to this one, and this equals to A magnitude. So I'm right? I proved that if you have a density matrix expressed as AI plus A dot sigma divided by 2, the length of the A represents the expectation value of this NA dot sigma. It represents the expectation value of this NA dot sigma. Okay, that is the first thing, right? Okay. Now, then what do I mean, right? So again, for each density matrix, rho correspond to different ensembles, right? You can have many mixed states. For example, 50% of 0 plus 50% of this, these are two pure states. You will get the same density matrix as 85.36% of this state plus 14.64% of this state. Okay, now, and then one of them has the mixed state orthogonal to each other. For example, in this case, these two are orthogonal to each other. It's just like the case of 0 and 1 orthogonal to each other. Okay? So, if that is the case, and I call this the red state, then A in this one represents the direction of this state on the Bloch sphere. So A is just like you have these two pure states and you represent the direction on the Bloch sphere. And the length of A is just the expectation value of this one on this scale. The normalized A dot sigma. This is difficult to understand. Let's take a look at this figure again. I hope that I can explain it clearly. On the left, it is a pure state, and we already learned that this A is the Bloch vector. The A is going to be 1, right? Because it's a pure state. So the length is going to be 1. And of course, since it is 1, then of course NA equals to A divided by the A magnitude is equal to A divided by 1 equal to A is just equals to itself, right? That is just the meaning of this. Then the A is this point. Then of course, then what is the A, or let me still call it NA dot sigma. NA dot sigma will be correspond to this direction, right? Because as we learned earlier, this NA dot sigma represent the expectation value along this direction, right? So then, of course, yeah, NA is the expectation value along NA dot sigma. Now, for a mixed state, then it will be different. And I told you that for each mixed state, there are many possible mixture that can give you this mixed state. But one of them will give you the orthogonal state. And this orthogonal state will be along this NA, this Bloch vector, right? It is short, but when you normalize, NA is like here. But along this state, it's just like I have a state here, I have orthogonal state here. They are orthogonal to each other, and they give the same density matrix as what we were given. And the length of the A is the expectation value of the given state for this operator, right? Which is the trace of NA dot sigma times rho. I'm not sure this one is important or not, but this is a good way to understand. It's complicated if you don't fully follow the math. I would like you to be able to follow the math, but I don't need you to be able to prove it. But the main point is that we have used a lot of math that we learned before. This is a good practice. Another thing is here I show you that the Bloch vector, once you represent the density matrix in this way, this Bloch vector really represents the state that you have. And it is and its expectation value and the expectation value along A dot NA dot sigma just is equals to the length of A. Okay, so here the summary, you can take a look for the class that we had earlier.